Right, we are going to be starting a new unit on momentum. And normally, a unit like momentum would start by looking at what are the equations, how does it relate to previous things. And one of the things that I want to do, though, is make clear to you why we need to study momentum, what purpose it serves. Because it doesn't do anything new in the sense of whatever we use momentum to do, we could use energy, or we could use forces to do the same thing. So in a lot of ways, it augments or replaces these concepts or these techniques. So we can do whatever we want to do. Whatever we've done in the past, we could use energy to do. Whatever we've done in the past, we could use forces to do. Momentum gives us another approach to take to try to solve things. And there are particular sets of experiments or particular sets of situations where momentum is much more useful or much easier to use than energy or forces. So what I'm going to do is start off by showing you a couple of those situations. Alright, this is a video clip from a YouTube video, and what we're going to see is off this side of the screen there's going to be a car coming into view, and we're going to see what happens. Okay, so what we saw was that the car came into view along this side, and another car was going this way, and when they collided, they both moved sort of in this direction, kind of a mixture of the two directions that the cars were initially going in. There was some twisting and turning, but we're not going to get into the twisting and turning aspects right now. We're just going to get into the motion of really the center of masses of the objects. This would actually be very, very difficult to analyze using energy, for instance. One of the reasons is because you're losing a lot of energy. So they start off with kinetic energy. This car also has kinetic energy. But during the process of the collision, a lot of that kinetic energy is transferred into heat, into sound. So we're going to lose a lot of the kinetic energy that was initially in the system. Now, if we have a satisfactory way to account for how much sound energy was generated or how much heat was generated by the collision, then we could certainly use conservation of energy to account for everything that happens. The problem is that in a situation like this, energy is very hard to use effectively. Not that it isn't true still, not that conservation of energy doesn't hold, but that it's very difficult to use it in this particular case. I have here on Interactive Physics two boxes. This one's going at 4 meters per second to the right, this one's going at 6 meters per second to the left. The mass of this one is 4 kilograms, the mass of this one is 1 kilogram. And what we're going to see is another collision. One of the things that is very difficult to analyze in a situation like this is using forces. So in addition to the difficulty of using energy, it's also very difficult to use forces. The reason is because of the time frame over which this all occurs. If we try to step frame by frame through this, we see this is the collision, and then they're not in contact with each other anymore. If we had a lot of different frames to show the collision step, then we might be able to use forces to analyze this. But because the collision takes place in the space of one frame, it's very difficult to see it. And actually, I've run this simulation or similar situations to this, and sometimes you don't even see the collision. You see the just before the collision and the just after collision. So you completely miss the collision. Some might say, well, that makes it so that the collision didn't actually occur. This is, of course, not true. We can see the effects of the collision, the differences in their motions from before the collision to after the collision. So we know that there were forces being applied. We know, for instance, that there was a force being applied to this one to the left. We know that there was a force being applied to this one to the right because we can see the results. But we don't know the size of the forces. We don't know how long those forces were acting. So it's very difficult to determine how much acceleration there was or anything of that nature. And to kind of show you what we do, I'm going to update this. One thing that we can do is try to extend the time over which a collision takes place. So initially these two were separated this same distance, but there was no spring in between them, so there was no collision, no collision, no collision, and then they hit each other. And the collision took place in a snap. What this does is it extends the collision time. So we can actually measure, obviously after the collision occurs, it's not quite accurate to what happened previously, but what we do see happening is leading up to the collision, and even that initial phase right afterwards before we max out the spring length again, we see the forces that are involved. So we can actually measure what's taking place force-wise over an extended distance, over an extended period of time. And so it becomes much more possible to do a force analysis or to do an energy analysis. Unfortunately, if you think back to that car accident, while there is something called the crumple zone in the car, which does extend the time over which the collision occurs, that time extension is very, very small. We're still talking very, very short periods of time over which the collision occurs. And it's not enough. It's very difficult to tell what happens. So momentum was in large part developed and used. It's used and prioritized as one of the major concepts in physics because of how useful it is in dealing with situations like this, where you don't know what's happening in the interaction. Maybe it's a very large force initially and then it peters off as the collision continues. Maybe it's initially a very small force and then it builds up and then it peters off again, sort of like that spring case. The thing about momentum is that it doesn't actually care about the details of what happens between these two objects. What it cares about is what was the initial state, and then it will tell you what the final state will be. Or for car accidents, let's say this is the final state. What it can do is it can help you determine what the initial state was. So that's going to be one of the things that we'll be looking at, is how can we use the concept of momentum to help us determine what happened prior to a collision, or vice versa. This is the state before the collision. What will happen after the collision? So it's kind of like a end around. We could use energy, we could use forces to analyze this, but it's easier if we use momentum. Okay, so when to use momentum. This should give you some pointers on when it's appropriate. First of all, when objects are in motion. If the objects are not in motion, then momentum has nothing to do with it. You can see that there is a link even just between those two words. Movement, motion, momentum. They're all very, very similar words. Momentum has to do with motion. So if the objects are not in motion with each other, there's no point in trying to use momentum. Another thing, though, is that if there are other energy types, then it's not normally a good idea. So when kinetic energy is really the only conservative type. And what I mean is that it normally doesn't pay to use momentum as your primary tool if there are things like gravitational potential energy or spring potential energy. We don't really use momentum in those cases. At least we can't use momentum by itself. So we might be able to use conservation of energy to convert gravitational potential energy into the kinetic energy of an object. And then if that object collides with something else, we would throw in a momentum situation. But if there is spring potential energy or gravitational potential energy, it doesn't normally pay to use kinetic energy. Another time when kinetic energy is very useful is when delta T is small. So if the time frame over which we're talking about is very small, then momentum is really a good tool to use, because it doesn't care if you can't see what's really happening during the collision. Number 4, collisions and explosions. These are the types of situations where momentum comes really in handy. So when you're talking about atomic motion, if you're talking about pressure of gases, a lot of times it pays to use momentum as your primary tool, because momentum has to do with the collisions between the molecules. If you're dealing with explosions, once again, they happen over a very small time period, and all of the energy goes into kinetic energy. So it kind of fulfills these types of things, and obviously with an explosion, objects end up in motion. The idea behind an explosion is that you're starting off with energy stored in one of these things, maybe as spring potential energy, let's say, and it then converts into kinetic energy. Momentum is sometimes not enough to handle that by itself, but I'll try to show you some cases when it actually would be. So just to do a quick rundown, when objects are in motion, that's kind of an absolute condition you need in order to use momentum. They don't have to always be in motion, but at some point they need to be in motion. When kinetic energy is your primary type of energy involved, when delta t is small, it makes sense to use momentum because it's very difficult to use energy and forces in those types of cases. And when you have collisions or explosions, which kind of by definition are when you have these small changes in time. So those are the main areas where you're going to use momentum. Typically also, if you're dealing with a collision or explosion, you want external forces to be minimal. What this means is something like friction. In that interactive physics example, friction didn't play a huge role during this very small change in time. So friction might be a substantial force for the overall motion of those boxes, or it might be a substantial force for the overall motion of the cars that we saw initially. But in the time frame of the actual collision that took place, the forces involved with the collision were very, very large compared to the forces involved with friction, so we're able to ignore the frictional forces.